Find the equation of the parabola described below. Find the 2 points that define the lattice rectum and graph the equation. So we're given that the focus is at -1, 0, and the directrix is the line x equals 1. Before we get into this, I really want to take a look at what the features of the parabola are so that we know how to relate these things to each other. So I'm showing a picture of a parabola with the orientation that I call opens up. And what I want you to notice are these special features. We have the vertex right here, which is the minimum in this case. It's also the place where the graph changes from decreasing to increasing. Then inside the parabola we have the focus. And the focus is a distance of A away from the vertex. In this case, because the parabola is oriented up, the focus is up from the vertex. Then we have the directrix. And the directrix, you can see, is running perpendicular to this line that connects the vertex and the focus. And the directrix is also A away from the vertex. So this distance, this perpendicular distance right here, is A. So this is the equation right here, which gives us a parabola that's oriented up. That's this one here is a parabola that's oriented up. And the squared is on the x, and we have a positive on this side over here of the equation. When we put a negative instead of a positive, so the squared is still on the x, but we have a negative, this is the orientation that is down. And then over here we have some equations where the squared is on the y, and when the squared is on the y, you have a parabola that's oriented either left or right. So when we have a positive, it's to the right, and when we have a negative, it's to the left. One more thing I want to point out to you is that we also have something called the lattice rectum. And the lattice rectum will be points that are in line with the focus. These are points that are on the parabola, and they create this line segment going through the focus. So because they go through the focus, they're going to share some of the coordinates from the focus. In this particular example, the y-coordinate of the focus will be the same as the y-coordinate on these 2 points. However, if your parabola is oriented, say, to the right, our focus will be here, and our lattice rectum points will share the x-coordinate with the focus rather than the y-coordinate with the focus. With all that in mind, let's give this problem a try. For this example, we're given that the focus is at -1, 0, and that the directrix is the line x equals 1. So the first thing I want to do is figure out the orientation of this parabola. So drawing my picture, this is just a sketch of the picture. If I have a focus at -1, 0, that would be here, and the directrix being the line x equals 1, I know that the parabola will be oriented to the left. And that's because the focus is going to be inside the parabola, and the directrix will be running perpendicular to the connection between the focus and the vertex. I also know that the vertex is at 0, 0. And that's because the distance A between the vertex and the focus is the same distance between the vertex and the directrix. So my focus is at -1, 0, and my directrix is the line x equals 1. Halfway in between those two, we have the vertex, which is going to be at 0, 0. So what we know is that we have a parabola that's oriented left that has a vertex at 0, 0. So this helps me know which equation to start from, which equation template. So we're going to start with y minus k squared minus 4a times x minus h. And we know that because the vertex is 0, 0, my h equals 0 and k equals 0. And a is the distance between the vertex and the focus, and that distance is 1. So we're going to be able to substitute these values into the equation template to get y minus 0 squared equals, I left off an equals up here, equals -4 times 1 times x minus 0. That gives me y squared equals -4x. So that's the equation of the parabola with a focus at -1, 0 and a directrix at x equals 1. Let's draw a little bit more detailed picture. So we said we have a vertex at 0, 0, a focus at -1, 0. The directrix is along the line x equals 1. And I want to find the lattice rectum points. The lattice rectum points will help me to draw how wide this parabola is set. So remember that the lattice rectum points, I'm going back up to my sketch for a second. My lattice rectum points are going to fall on the same line with the focus. So with this orientation of being left, it's going to share the x-coordinate with the focus. So the x-coordinate of the focus is -1. So I'll take the equation that I found previously and substitute a -1 and solve for the y. So -4 times -1 is +4. I can square root both sides to get y equals plus and minus 2. So our lattice rectum points are -2, -1, and oops, I've got my coordinates backwards there. -1, -2, and -1, +2. Let me mark those on the picture. -1, 2, and -1, -2. So now I can sketch the graph of the parabola. Oriented left, with a focus at -1 and a directrix of x equals 1. The graph of an ellipse is given. Match the graph to its equation. we're given this picture here of the ellipse. Before we start working this example, let's take a look at some of the features we need to pay attention to. So we've got two orientations of an ellipse that we need to pay attention to. And that's the vertical orientation and the horizontal orientation. So I've listed the two equations here. And the first equation is the horizontal orientation. And the second equation is the vertical orientation. Now, the way that I can tell the difference between the two orientations is with the value of A. I'll go into a little bit more details about that when we look at the picture, but A is always the largest value among the three, A, B, and C, for ellipses. So with A underneath X, we have, or the larger value underneath X, we have horizontal orientation, and the larger value under Y is the vertical orientation. Now I've drawn a picture of the vertical orientation. So this picture is the vertical orientation. And with the ellipse, you have a center, which we label with HK. And because this is a vertical orientation, we're going to focus along the vertical axis for most of the important features of this graph. And what you'll find is that we have foci that are above and below the center, equal distance, that distance of C away. So the distance between the center and the focus is C. And then a little bit further along, we have two vertices. Those vertices are equal distance, a distance of A. So the distance between the center and the vertex is A. And then going perpendicular to that, we have what we call the minor axis. And these minor axis vertices, and those will have a distance of B from the center. So if we were to have an ellipse that had a horizontal orientation instead, you would have a center. A little further out, you would have foci. Those foci would be C away from the center. A little further out, you would have your vertices, and those would be a distance of A from the center. Then going in the perpendicular direction, you'd have your minor axis vertices, and those would be a distance of B away from the center. Now remember I mentioned that A is always the longest, so I've drawn B to be closer to the center than A. And then you can see a horizontal orientation of the ellipse like that. One last thing I want to share with you all is that if I connect this focus to the vertex over here, that creates a right triangle. And with a little bit of figuring out, you can figure out that this side has a length of A. And we have three sides of a right triangle. We know Pythagorean theorem allows us to relate those sides. So we can say that B squared plus C squared equals A squared because of the relationship between those sides. And that's why you see these equations next to the equation of the ellipse, because those sides can be related to each other. Now we can try this problem. The graph of an ellipse is given. Match the graph to its equation. So for this example, we can see that this ellipse has a vertical orientation. So we know that we're going to use this equation, the second one, x minus h squared over b squared plus y minus k squared over a squared equals 1. And then looking at the graph, we can figure out what A is. We have a center at 0, 0, and these vertices are here and here, and we can count 1, 2, 3, a distance of 3 away, so A is equal to 3, and then going in the horizontal direction, we can see that that's 1 unit away. Our minor axis vertices is 1 unit away, so B is 1. And with that information, we can work out our equation. So let's fill in the blank here. We have x minus 0, because the center is at 0, 0, over 1 squared, b squared, plus y minus 0 squared over 3 squared, that's a squared. And we're going to simplify that to become x squared over 1 plus y squared over 9 equals 1. And then finally, x squared over 1 is 1. So we have x squared plus y squared over 9 equals 1. And that is the equation of the ellipse that is shown in this picture. Find the vertices and foci of the following ellipse. Graph the equation. Our equation is x squared over 9 plus y squared over 36 equals 1. Before we start this problem, I want to take a minute to look at a picture of an ellipse and make sure we understand all the features. So at the top here, I've listed equations that represent the two different orientations that we're going to focus on. And the two orientations are horizontal and vertical. And the reason why I've labeled them in this way is based on the value of A. A is always going to be the longest of the three of A, B, and C because it's the distance between the center and the vertex. So when we look at one of these equations, if we see the larger value under X, we have a horizontal orientation, or the larger value under Y, we have a vertical orientation. I'm showing you a picture of the vertical orientation, and I want to point out just a couple key features. I've already mentioned the distance between the center and the vertex is A. The distance between the center and the minor axis vertex is B. And then we have the distance between the center and the focus is C. If I draw a line connecting the focus with the minor vertex here, that creates a right triangle. And we can figure out that this distance along the hypotenuse is A, the same A that is the distance between the center and the vertex. And that's where these equations come from right here. Because we have a right triangle, we're able to relate the sides of that triangle with Pythagorean theorem. So we get that b squared plus c squared equals a squared. Now getting back to our question, we want to find the vertices and foci of this ellipse. And with this equation, I can see that the larger number is under y, meaning that I'm going to have a vertical orientation. So the 36 will match with a squared, and so that means that a is 6. Then 9 will match with b squared, so that means that b equals 3. And I can also see that there are no numbers added or subtracted here, so this ellipse has a center at 0, 0. I also want to find the value of c so that I can locate the focus. So I'm going to use this equation, b squared equals a squared minus c squared. So b squared is 9, a squared is 36, minus c squared. I'll subtract 36 on both sides. 9 minus 36 is negative 27, equals negative c squared. I'll divide both sides by a negative 1. That gives me c squared equals 27. If we square root both sides, we get that c equals square root of 27. I'm ignoring the negative because c is a distance. We could simplify this. 27 is 9 times 3. So c equals 3 square root of 3. I like to use the picture to help me figure out where the vertices and foci are. We have an ellipse that has a center at 0, 0. And since A is 6, and this ellipse is vertically oriented, I'm going to go up and down 6 units from the center. Up 6 and down 6. So I used the fact that the orientation was vertical, as well as the value of A, to find the location of the vertices. So I have 2 vertices, and those are at 0, 6 and 0, negative 6. Now the foci will also be located vertically up and down from the center. And I put in my calculator 3 square root of 3, and that's approximately 5.2. So I'm going to go up and down from the center about 5.2 to about here and here, and that's the location of my foci. So my foci will be at 0, 3 square root of 3, and 0, negative 3 square root of 3. Then I'm going to use the value of b to show how wide this ellipse is. So b is 3. So I'll go 3 units away from the center, left and right. And now I can sketch the graph of the ellipse, passing through the vertices and the minor vertices. The graph of the hyperbola is given. Match the graph to its equation below. So we have this picture of a hyperbola, and we want to match it to one of these equations. Before we do that, let's take a look at some of the features of a hyperbola. So first, we have 2 orientations that we're going to focus on, and I've written the 2 equations that match those 2 orientations. And those orientations are horizontal and vertical. Focusing in on the equation, the way that I can tell the difference between the horizontal orientation and the vertical orientation is by which term is positive. So in this first equation, the term that contains x is the positive term and y is the negative term. So with x being the positive term, we have a horizontal orientation. In the second equation, the y is the positive term, and that is with the vertical orientation. Then I've got a picture over here of our hyperbola, just to give you an idea of the features we want to pay attention to. All of the major features are going to fall along the transverse axis. This picture I'm showing you is of the vertical orientation, and this vertical line is the transverse axis. If we had a horizontal orientation, our transverse axis would be horizontal. So along that transverse axis, we have the center, we have vertices, and the vertex will be a distance away from the center, and you can see that a is in both of those equations under the positive term. And then we also have foci, and those foci will be c distance away, so c distance away from the center is the foci. There are also asymptotes, and the asymptotes pass through the center. And they'll show you where the hyperbola will be drawn. So along the ends here, the hyperbola will be getting closer and closer to those asymptotes. If I were to draw from the vertex over to the asymptote where they meet, that would be a value of b. And b is on this part of the equation here. So from the vertex to that asymptote is b. We can do it with the other vertex as well. So it kind of creates a little box here. If we focus on one of these triangles that show up in here, you can see that we have A, B, and C along those triangles. This makes a right angle. So we have a right triangle, and we can use Pythagorean theorem, and that's where these equations come into play. You can see that a squared plus b squared equals c squared. With all that in mind, let's take a look at this example. We have the graph of the hyperbola, and we want to match it to one of these equations. So I can see that this is a vertical orientation of the hyperbola. We have a vertical transverse axis, and I can see where my vertices are. I have a vertex at 0, 6 and 0, negative 6, and my center will be at 0, 0. So this tells me that A is equal to 6 because the distance between the center and the vertex is 6. So I'm looking for a vertically oriented equation where A is 6. So a vertically oriented equation will have the y being the positive term. So these two have y being the positive term. I can eliminate these two that are horizontally oriented. And because A is 6, this will be the right choice. Y squared over 36 minus x squared equals 1. Find the equation for the hyperbola described. Graph the equation with center at 0, 0, focus at 3, 0, and vertex at 1, 0. So for this example, we're given that we have a center at 0, 0, a focus at 3, 0, and a vertex at 1, 0. And with that information, I'd like to sketch the graph to find the orientation. So we have a center at 0, 0, a focus at 3, 0, and a vertex at 1, 0. So because all three of these points are falling in line horizontally, I know that this will have a horizontal orientation. This first equation is the equation of the horizontal orientation because the x term is positive. I can also tell a few other pieces of information. A is the distance between the center and the vertex. So the center and the vertex have a distance of A, which in this example is 1. Then the distance between the center and the focus is C, and that distance is 3 for this example. Then we can use this Pythagorean equation to find the value of B. So B squared is equal to C squared minus A squared. B squared is 3 squared minus 1 squared. B squared is 9 minus 1. B squared would be 8, and B equals the square root of 8. I can write the equation of the hyperbola now. So using the template for the horizontal orientation, I have x minus h squared over a squared minus y minus k squared over b squared equals 1. Our center is 0, 0, so h and k will be filled in with 0. A is equal to 1, and b is equal to the square root of 8. So we have x minus 0 squared over 1 squared minus y minus 0 squared over square root of 8 squared equals 1. And that simplifies to be x squared minus y squared over 8 equals 1. So now I'll draw a more detailed graph of the hyperbola. So we have a center at 0, 0, a focus at 3, 0. So that means we have another focus at negative 3, 0, a vertex at 1, 0, and another vertex at negative 1, 0. And then from there, we really need the asymptote to help us know how to draw the hyperbola. So I'm going to use, first of all, square root of 8 is approximately 2.8. And if we look at the asymptote is going to have a slope of b over a. That's 2.8 over 1. So from the center, if I do rise over run, I'll find the value of my asymptote, or I'll be able to sketch the asymptote. So from the center, I'm going to rise 2.8 and run 1. That would be about right here. So I can draw one asymptote that passes through the center and has a slope of 2.8. And then I need to also have one with a negative b over a. So it's a negative 2.8 over 1. So I'm going to go down 2.8 and over 1 would be about right here. Connect those 2 points to give me my other asymptote. So it's connecting the center with a slope of negative 2.8. And then I'll be able to draw my hyperbola starting from the vertex and following the asymptotes. Starting from the other vertex and following those asymptotes. Let me fix this one here. Kind of stopped following the asymptote.